Welcome to Susan and John MathTube. In this video, we'll be discussing about the basic things in vector algebra that you already learned in class 12, and we will discuss the basic stuffs about triple product. Okay, so in mathematics, when we learn vectors, what we do is we imagine a directed line segment. But basically, you have to understand, a vector means we are representing quantities which has both magnitude and direction or direction. Maybe in class 6 or class 7, when you started learning ordinary algebra, you started representing things with the or real life scenarios into variables. For example, let the price of something be X. Let the weight of something be Y. Let the area be A. That is how we started algebra, right? Long back. Similarly, in class 12, when you learn vectors, you learn that you are representing, this is actually a mathematical method of representing things which has both magnitude and direction. For example, and the best example is force. Suppose you want to think about force, you can see that there are two things involved in it. The amount of force applied. That amount is called magnitude, the quantity. And second thing, when a force is applied on an object, there will be a certain direction. For example, suppose that you take a hammer and you want to hit a nail. So there will be a direction, right? You cannot hit anywhere and say that you hit that nail. Or there will be specific direction, and there will be specific amount of force that you apply. Now just imagine you're opening a tap or a bottle cap, or let's say you started any engine, so the pistons will start moving. So there will and it will create rotational force. So basically everywhere we are able to see that we are dealing with two things, magnitude and direction. In mathematics, what we do is we generalize this by imagining a vector quantity to have both magnitude and direction and denoting it by a directed line segment. And of course, the length of the vector will represent the amount, the magnitude, the modulus, and the arrow will represent the direction. Okay, so what I'm trying to convince you is we are systematically analyzing vectors in mathematics. But another thing, we do not care whether you're going to use vector in physics or in economics or in any subject, maybe in mechanics. You can use it anywhere. Only thing is, the quantity under discussion should have two things: an amount, that is magnitude or modulus, and a direction. So you can use it in economics, you can use it in physics, you can use it in mechanics, wherever you want to use it. But when it is in mathematics, just like the variables you learned, come on, think about it. You learned about differentiation in maybe class 11 or 12. You learned about defining functions. But the concept of differentiation, integration is used by statisticians. It is used by people who do physics problems, and name it, it'll appear anywhere. But when you learn it in mathematics, you just generalize and call it X, Y, W, etc. You do not care what is X, etc. So the same thing happened. We are generalizing stuff which has both magnitude and direction. Okay, now let's move on. Now look at this. A vector, as I told you before, has two things. One is a length. Length is magnitude or modulus or the amount involved in the vector. And second is a certain direction. And we denote vectors by A. And in some books, what they do is they do not put arrow mark, but they put bold like this. They make it like A into a bold alphabet. But in examination, this is not feasible. This will be better. So just put an arrow mark. And even some people use just a bar for vectors, not even arrow, just a bar. If you want, you can follow that also. And sometimes we define vectors with the help of endpoints, the terminal points. So suppose this is capital A and capital B, we can define the vector to be A, B. Okay. And now remember, vector and the concept of direction ratios are the same, or let's say analogous. If you want, you can check out that videos. I have kept the concept of direction ratios, direction cosines, etc. It's kind of like analogous. Okay, so basically, if you want to define a vector, we do that with the help of its projections. And if you want to understand, it will be very easy for you to understand in two-dimensional vectors. Let's say this vector has projection 3 units along the x direction and 2 units along the y direction. That means the name of the vector will be 3i. And remember, I stands for 1 unit movement in the x direction. And 2 stands for 2 into j. So what I understand is the required vector has a projection of 3 units in x direction and 2 units in y direction. Now in 3 dimension also the same thing happens. I'll repeat again. You can check out the videos in which I put all the graphics, etc., so that you can see the projections in 3 dimension also. It's very hard to do this without a graphical software, but you can check it in the 3D videos. Okay, anyway, you have to understand there are 3 projections here. One along the x direction and another along the y direction, and the third one will be along the z direction. So if the projections are respectively, let's say 1, 5 and 4, then the name of my vector or my vector will be 1 into I plus 5 into j plus 4 into k. Now remember, whenever I talk about the vector 3i plus 2j, you can create it very easily. If you want, you can create it from the origin. Look at this, 1 unit, 2 unit, 3 unit. And then you go up 2 units. And look, this is your vector. At the same time, another person can create the same vector a little bit to the right or up or down or anywhere. Look, I can create the same vector here. 1 unit, 2 units, 3 units, and up I go 2 units. See, I get the same vector. So remember, the vector that we learn or the vector under discussion is called translation vectors. Or we understand that when you see a vector in the form 3i plus 2j or 5i plus j, etc., etc., we are talking about any of the vectors which is in a parallel system. That means the vector that I imagine and you imagine need not be same, but they might be parallel. Okay, so I'll make things a little bit easier now once more. In mathematics, vectors mean a quantity which has both magnitude and direction. And mathematicians consider vector to be a directed line segment. So the magnitude part or the amount of the vector will be defined with the help of the line and line segment, and the direction will be denoted by an arrow. Okay, now vectors are denoted by A with an arrow or a bar or even bold letters or using the initial and terminal points, etc., etc. And the length of a vector will be denoted by the symbol modulus of A whenever you need clarity, or simply by A whenever things are like very clear. I'll repeat once more. You might have seen this in physics book. Whenever you talk about force, pressure, etc., your teachers will use that in 2 different ways. When you see they are using an arrow, they are talking about the actual vector, and when they are using like only F, they are talking about the amount in the vector, the magnitude. Especially when you learned about work done, etc., you might have seen the difference between F vector and F. So remember, if you want more clarity, you can call the modulus to be, or the magnitude or the amount to be modulus of F, or simply denoted by f. Okay, the next thing, vectors are denoted with the help of the projections. So if you know the respective projections made along the x-axis, y-axis, z-axis, you can define a vector to be the projection along x-axis into I plus y-axis into j plus z-axis projection into k. So the same concept is used as direction ratios in 3D geometry, or let's say it's kind of like analogous to this concept. Okay, now the next thing you should understand is the concept of position vectors. This is very, very important. The concept of position vectors. So look at this. When you learn 2D geometry or 3D geometry, we are taught that the two-dimensional plane or the three-dimensional plane consists of infinite number of points, and every point will correspond to a coordinate, right? Okay, in vector geometry, what we are taught is slightly different. We are taught that this whole plane comprises of vectors, so many vectors. Okay, I'll tell you how they are connected. In 2D geometry, you learn that the two-dimensional plane is full of points, right? But in vector geometry, we learn that every point has a position, and that will be called the position vector. And the position vector is accomplished by drawing a line or drawing a line segment or drawing a vector from origin to that point. Okay, I'll give you an example. Look at this. Suppose we have a coordinate, let's say 1, 2, 3 and 2 units up. Okay, so this coordinate will be 3, 2 in our two-dimensional geometry. But when we learn vector geometry, we call this the position vector. Look at this. Can you see how did I create the position vector? Instead of the point in two-dimensional geometry, just join it with the origin. Okay, come on. Now tell me, what are the projections? What are the projections made by this position vector? It's very simple. The projection along the x direction will be 3 and along the y direction it will be 2. So in vector geometry, we imagine this point to be the vector 3i plus 2j. So once more, let me try to convince you this concept called position vector. Look at this. When we learn 2D geometry or 3D geometry, we learned that the two-dimensional plane or the three-dimensional plane is made up of infinite number of points. But when we learn vector geometry, we understand that each point corresponds to a position vector. And if you want to understand what's a position vector, it is very simple. It is a vector connecting the origin and the point in consideration. And the coordinate of the point, suppose this point has coordinate like 3, 4. The coordinate of the point will help you understand the projections. The coordinate of the point tells me there is a 3-unit projection in the x direction. So I know that the position vector is 3i plus 4j. I hope that is clear. Okay, now let's go to the next very, very important thing that you should understand. Now imagine you know 2 points in the plane and the vector created by the 2 points. So let's call the points capital A and capital B. But wait a minute, just now I told you every point in the 2-dimension or 3-dimension corresponds to the position vector. So how do you create the position vector? Join the point with the origin. So this is the position vector of A and this is the position vector of B. Now remember, in vector you have already learned what you call addition law, etc, etc. So using those things, we can understand that AB vector is nothing but the position vector of point B minus position vector of point A. So once more, let me make it very clear. If 2 points are given in space, if 2 points are given in 2-dimensional or 3-dimensional or 4th-dimensional or whatever be space, the vector connecting A and B in the direction of AB is given by OB minus OA. Okay, let's brief everything. So once more, Mathematicians what you call consider vector as a quantity which has both magnitude and direction. And in mathematics, we learn vectors as directed line segments, where the length of the line segment will be the amount or the magnitude or the modulus of the vector, and of course the arrow will denote the direction. Vectors are denoted by A, or what you call bold letter A, or using the terminal and initial points AB, etc., etc. And the amount involved in the vector, the magnitude of the vector, can be clearly denoted by the symbol modulus of A. So remember, modulus of a vector refers to the length of the vector. And in casual situations, we can write the modulus to be simply as A. So remember, writing A or modulus of A implies the length of the vector. Okay, now the next thing I want you to understand is unit vector. I forgot to tell you in the beginning, but I'm sure you might have heard about unit vectors. Actually, the concept of direction cosines. So in unit vector, what we do is we take a vector in the same direction of the original vector, but we cut its length in such a way that there will be only one unit length. For example, if this vector is of 5 units length, let us say this vector is of 5 unit length. Just imagine I'm going to cut it into 5 equal parts. How many equal parts? 5 equal parts. And then each part will act like a unit vector. Or I can create one unit length vector in the same direction parallel to this. And remember, unit vectors are denoted by hat, a hat. If you see hat or cap, you can use the word hat or cap. Then we have to understand that it is a vector in the direction of A, but the length of this vector will be 1 unit. Okay, now the vectors I, J, K, which I was referring earlier, because I know you have already learned this in your grade 12, grade 10, etc. So remember, if you move 1 unit in the x direction, we do not denote it by x cap, we call it I cap. And if you move 1 unit in y direction, you should use j cap. And if you move 1 unit in the z direction, then you should use k cap. And by the way, normally I told you in books they use cap, and in some books they use thick alphabets for I, J, K. That's also okay. But never ever use this bar. It will put people in what you call confusion. Unit vector should be always denoted by cap or hat. Okay, then now the next thing. Now look at this. Now we have a very interesting concept that is called position vector. In 2D geometry, we learned that, or in 3D geometry, we learned that the space is made up of infinite number of points. In vector geometry, what we do is, instead of learning the space is made up of points, we learned that the space is made up of infinite number of vectors. And those vectors are called position vectors. For example, if a point in 2D geometry is like what you call, as you see in the picture, then in vector geometry, we are supposed to imagine this particular vector. In 2D geometry, if you see a point like this, then in vector geometry, we imagine a vector which joins the origin and that point. In 2D geometry, if you see a point like this, then in vector geometry, we imagine the vector joining the origin and that point. I hope you understood the concept of what you call position vector. Now remember, let's say this vector is like what you call 6, 2. So the okay, imagine this point is 6, 2, or the coordinate is 6, 2. Then the position vector will be 6i plus 2j, because I know the projection of the vector along the x direction will be 6 units and the projection in the y direction will be 2 units. Okay, now the last thing that we discussed is, suppose 2 points are given in the 2-dimensional plane. Then the vector joining A and B in the direction of AB is given by the position vector of B minus position vector of A. Okay, that's these are the things that you learned long back. Okay, now I need two more things so that we can define triple products. We can add vectors, and it's simply like the algebra you learn. Okay, and we can subtract vectors, but remember the meaning is different. Addition of vectors is called resultant of a vector, because practically vectors are related to force and other stuff. So basically, let's say you have an object here and you're applying a force in this direction and you're applying a force in another direction, and you can see that the second force is a little bit more than the first force. So according to the first force, we expect the body will move in this direction, and according to the second force, we expect the body to move in this direction. But basically the body will move in a third direction, and the amount of force generated will be actually a little bit less than F1 and F2. And if you want to know how much amount, then you have to do vector addition. So remember, the concept of vector addition is completely different, even though the algebra looks same. For example, if I want to add the vector 3i plus 4j and 2i plus 7j, in mathematics it looks just like simple addition. But remember, the new vector which is generated, the sum vector which is generated, represents the resultant. Okay, now I need one more thing, that is multiplication of a vector by a number. So look at this. When you do this operation, we can understand that we are talking about magnified vector. So look at this. We are talking about a vector which is 5 times the original vector. So we can understand that the length of the vector has increased. And if you multiply by some fraction like 1 by 2, then I can understand that the length of the vector has decreased to half. So basically, when you multiply a vector by a number, you should imagine about magnification of the vector or shrinking of the vector. Okay, now the next thing is the two important operation that you have learned, that is called the dot product and the cross product. So remember, vectors do not have multiplication, just like number multiplication. But instead, they have introduced two operations. One is called the dot product or the scalar product, and another is called the cross product. Okay, dot product is very useful when you are considering one vector in another direction, or if you want to learn the effect of one vector in another direction. For example, if you are learning about resolution of vectors, or if you are learning about how a vector will be affected in another direction, etc., etc. For example, let's say a person is pulling a thing in this direction and the object is moving in this direction. Look, so someone is pulling in this direction, so the direction of the force is here and the body is moving in another direction. So in such cases, you will need dot product because you will be taking projections. Now remember, mathematically the dot product is a scalar. That means if you take the dot product, you're going to get a number. And formula wise, it is given by the formula modulus of A, modulus of B, and cos of the angle between the vectors. And similarly, in cross product means cross product is very important. That is actually the creation of a vector perpendicular to two other vectors. Okay, so imagine we have two vectors in a plane. So basically, the cross product gives a third vector, or the cross product is a vector which will be perpendicular to both the other vectors. Is that clear? So imagine we have two vectors, and then you can imagine cross product to be a vector which will be perpendicular to both the other vectors. Anyway, it's given by the formula mod A mod B sin theta multiplied by n cap. Now n cap refers to the normal vector. N cap refers to the normal vectors, because I told you this is a number and this is the vector which will be perpendicular to both. Okay, now we have some alternate formulae also. Suppose A and B are given in component form. Component form means, I already explained, a vector can be written with the help of their projections. So suppose A is the vector a1i plus a2j plus a3k, and B is given by b1i plus b2j plus b3k. Then you can use the formula a1b1 plus a2b2 plus a3b3. Now make it very clear in your brain. This is a scalar, and the output will be a number. You're combining vector and vector, but remember the output will be a number. And the cross product also has an alternative method once they give it in the component form, that is determinant ijk a1 a2 a3 b1 b2 b3. Okay, that's it. That's with the basics. Now what we do is we will define something called triple products. So basically the name triple product tells you we are going to combine three vectors. So just imagine we have three vectors A, B and C. Our job is very simple. We have to create a scalar, a number and a vector with the help of dot and cross. And don't forget, dot and cross are operations which will combine vector and vector. Okay, so look at this. Suppose I put dot here and dot here. Now think about it. If I find a dot b, then I told you it will be a number. And then let's say the answer is like 5 or 7 or 10, some number. Now look at this. Does this make any sense? No. Because dot product means we can combine only vector and vector. So if a dot b gives you a number, then this doesn't have any sense. So clearly this is not a triple product. Now let's imagine we have one dot and one cross here. This time I think it will work provided I put a bracket here. In the sense I'm supposed to do this first. So if I perform the cross product, then you know that I'm going to get a vector. Now A itself is a vector. Now does it make sense? Yeah, it makes sense. And look at the answer. Look, vector dot vector will give you a scalar, a number. So basically this is called the scalar triple product. Okay, once more let me tell you. We are thinking about creating triple products. And we want to create two triple products. One is called the scalar triple product and another is called vector triple product. Okay, so what we do is we take three vectors. And the operations that you're allowed to use is the dot or the cross. Now what I did is I put one dot here, I put one cross here. And I'm going to put a bracket in the sense I'm going to perform this operation first. So the cross product will give me a vector. A of course is a vector. So vector dot vector is going to give me a number, a scalar. So look at this. This is called a scalar triple product. Now remember, a scalar triple product is denoted by A, B, C. And it's what you call, it's called STP for convenience, scalar triple product. Okay, now I'll show you one more thing, one more very interesting thing. Suppose I take A, B, C and I put cross here and dot here. Do you know something? Again, if I put the bracket here, I'm going to get a vector here and this is a vector. So I'll get a scalar and amazingly, you'll get the same answer. So to construct a scalar triple product, it's very easy. Take three vectors A, B and C and put one dot and one cross according to your convenience. According to your convenience. If you want, you can take this as a cross and this as a dot. No problem. But one condition, the part which has cross product should be evaluated first. And that the number created here will be called scalar triple product. That's it. Okay. And how do you denote a scalar triple product? By using the notation box ABC. And another important thing, we have a shortcut to evaluate this. I'm just skipping the proof for the time being. Suppose they give you A, B, C in component form. Do you remember component form? Yeah. Every vector can be written in the form A1i plus B1j plus C1k. Another vector B will be B1i plus B2j plus C, like that. So let's say A is given by A1i plus A2j plus A3k. B is given by B1i plus B2j plus B3k. And C is given by dot dot dot. Same thing. Then the scalar triple product will be the determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. Or in other words, all the properties of determinants are also properties of STP. Okay, this has one geometrical meaning. This STP, if they are like what you call, an STP represents the volume of a parallelly piped. So parallelly piped means the three-dimensional version of a parallelogram. You can imagine like what you call, you know that what you call a square becomes a cube, a rectangle becomes a cuboid. Similarly, think about you're collecting so many parallelograms together. So the STP, if you calculate the STP, where ABC represent the what you call edges of the parallelly piped, then the STP will give the volume of the parallelly piped. We will discuss this in detail in the next video. Okay, now let me define another thing. So suppose I take three vectors. Now look at this. If I put a cross and a cross, and let's say I'm going to evaluate this first. Now remember, this is a vector. This of course is a vector, and vector cross vector will give me a vector. This is called vector triple product. So remember, we are defining something called VTP and STP. STP is so easy, you put one dot and one cross according to your convenience, but evaluate the cross product first. But remember, in vector triple product, the bracket must and will belong to the second and the third. So if you write A cross B cross C, I won't agree that this is a vector triple product. I will never agree that this is a vector triple product. So this is a vector triple product. Okay, let's make it short once more. Take three vectors. You put one dot, one cross, and put brackets for the cross product in the sense that you're going to evaluate it first. This is called the scalar triple product. Or you can write the scalar triple product to be A cross B dot C, and both are same and is denoted by box A, B, C. Now, when it comes to vector triple product, it is A cross B cross C. That's it. That's it. Okay. Now, I'll be back with more videos, and in the next video what we do is we will do a lot of problems based on this STP and VTP. So till then, my friends, bye.